Hello. I'm going to be giving a brief talk today on an introduction to digital filters. This is something that I've been kind of learning about on my own with the help of these very nice sources. Pretty much everything from this talk is stolen from this book by Julius Smith, which is available online, called An Introduction to Digital Filters. Also kind of pertinent to this talk are his other books, Spectral Audio Signal Processing and Physical Audio Signal Processing. And he also has one on the mathematics of the discrete Fourier transform. All good books. Aside from that, there's a book by Meinhard Mueller called Fundamentals of Music Processing. Very nicely written book with a bunch of applications. And this tome by Alan Oppenheim and Ronald Schaefer, kind of a reference text, Digital Signal Processing. Huge textbook. Okay, so what am I actually going to be talking about today? The main object that we're going to have in mind is a signal. And I'm always going to have audio in mind as the application for this talk. So you should think of a signal as an audio signal that's coming in. And I'm going to be talking about digital signals, meaning that everything has to be finite. And for us functionally, that means two things. It means everything has to be discrete, so functions have to be discretely sampled, and they have to be finite length. So a signal for us is going to be just a sequence of real numbers. And these will represent amplitude as a function of time. Okay, and just to give you an idea of the kind of time resolution that we have, the typical, or maybe not even typical, maybe standard, audio sampling rate is 44,100 hertz samples per second, meaning that the data that MP3 files and files like this have for their amplitude recording is every 1 second they have 44,100 data points representing the amplitude of the sound wave that's passing through. Okay, so we're going to be doing a lot of Fourier analysis in this talk. And I've already given a talk, which is not recorded, and I don't remember everything from it, on what happens when you discretize the Fourier transform. So I'm not going to be rehashing all of that, but I will give a very brief reminder of what happens to the Fourier transform when we discretize. So on the time domain, typically our functions live in L2 of the real line, but we have to discretize, and this gives us something that lives in L2 of the lattice, let's say, if we normalize our sampling rate to 1. And in addition to discretizing, we also need to truncate our signal, make it a finite length function, which gives us something that lives in L2 of the torus. Okay, and so these two things kind of commute. We can do them in either order, and either way, we get something that lives in L2 of, let's say, capital V, which is some capital N dimensional vector space, where capital N is the number of samples that we have. Okay, meanwhile, on the frequency domain, when you take the Fourier transform of any of these spaces, these actions of truncation and discretization are Fourier dual to each other. So Fourier transform takes L2 of R to L2 of R, but then discretization on the time domain corresponds to truncation on the Fourier domain. So this now is truncation, and this gives us something that lives in L2 of the torus, which is Fourier isometric to L2 of the lattice. And similarly down here, this is now discretization, and this gives us something that lives in L2 of the lattice. and then these still commute over here and give us something that's in L2 of the same dimensional vector space. Conventional. Okay, and these two diagrams are kind of isometrically mapped onto each other by the Fourier transform. Okay, to be a little more explicit, the Fourier transform of a signal x, so this is our input function, evaluated at a frequency k, is given by summing over all the samples in x of n e to the minus I k n. Okay, we're not going to focus too much on this formula, but one thing that I'll note from it that's very pertinent to the talk is that if x is real valued, which for us it always is, if we have a real valued signal, then if we evaluate the Fourier transform, and I should note a notation that I'm going to be using to denote this by x hat for short. The Fourier transform of x evaluated at k. So x hat of k, conjugate, if you put a conjugate over this guy, this is real valued, so nothing happens, and you just hit the phase. You get x of n e to the positive I k n, which is the Fourier transform of, or the Fourier mode at the opposite frequency, the negative frequency k. Okay. This means that, so i.e., x hat is a Hermitian function. Which means that its modulus, norm of x hat as a function of k, is even or odd? Even. X hat modulus is even, and the argument of x hat, meaning the phase, or the angle, is odd as a function of k. Okay. So, what's the picture of this phenomenon? Let's say, for example, we take an input signal which is sine of 2 pi 440 hertz, it's middle C, over 44,100. This is our sampling rate. If we look at the Fourier transform of this pure sinusoid resonating at middle C, let's look at the modulus of the Fourier transform. What we see, and this is a kind of cartoonish representation of the axes here, we get a spike at 440 because our Fourier transform should just be kind of the delta function at that Fourier mode. But also, if we keep going along, on the other side of the halfway point here, here's 44,100 hertz minus 440, we get, this is 0 all along here, and then we get another spike here. And we're periodic on this domain. So what's happened is, because our modulus is even, kind of only half of this data, only the left half is really necessary to determine the function entirely, and the right half is just a mirror image of it. And so typically, instead, we only draw up to half the sampling rate. Draw up to here, and then the rest is implied. We just cut off the picture there. Okay. And then the argument or phase or angle is exactly analogous, but instead of being even, it's odd. Okay. Oh, and a nice little remark here. There's some kind of preservation of information going on. When you're taking the Fourier transform, well, okay, so the Fourier transform is an isometry. And when you're going between finite dimensional vector spaces, that exactly means that the number of data points that you have on one side is equal to the number of data points that you have on the other side. There's like this, like the number of bits stays the same when you go between the time domain and the frequency domain. And so in the time domain, we have n real bits, and in the frequency domain, we have n over 2 relevant complex bits. Right, because you only need, you only need the 1/2 of the frequency range you would expect to reconstruct the function over there. Means you have n over 2 complex bits. Complex bits are 2 real bits. And if you're worried about, so a question you might have, what if n is odd, and then we can't divide by 2, how does this like number of bits little calculation work out? The answer to your question is something like some 0 mode, maybe more than 1, is redundant. So when you have an even function or an odd function, then your 0th Fourier mode, I forget for which, has to be 0. I guess it must be even functions. No. Well, one of them, even or odd functions, your value at 0 is always equal to 0, and so somehow that's the answer. Somehow it always works out. Okay. All right, now let's get into the actual kind of main subject of the talk, which is digital filters. So, for us, a digital filter is going to be something that takes an input, what do we call them? Signal. Takes an input signal and it maps it to some output signal. And it'll do something to the signal to make it sound different. And basically the main goal of this talk is going to be to understand, we're going to look at a certain class of filters and try to understand what these filters do and how to analyze them. Okay, so immediately, let's give an example of this class of filters. And I should mention, the output filter doesn't need to be exactly as long as the input filter, but for this talk it always will be. Okay, so let's let our output sample at time n be x of n plus x of n minus 1. So taking the sum of the two previous frequencies, or the two previous samples. Okay, so our goal is to kind of understand how something sounds different after we apply this filter. So once we get, if I take a song that's represented in x of n, what does it sound like when I pass it through this? When I get my output song y of n, what does it sound like afterwards? Okay, so let's immediately answer that question. First, by rewriting this as a convolution h convolved with x, evaluated at n, where h is this very simple function that's 1 here and 1 here, a discrete function, and it's 0 everywhere else. Right? You can see that this is exactly doing what my filter does here. So it takes this plus this and spits out at index n. Okay. Now we're in business, because once we have something in the form of a convolution, the Fourier transform takes that to multiplication. So y hat is x hat of k, or h hat of k times x hat of k. And this gives a very simple interpretation of what this filter does. So at every Fourier mode of my input signal, I multiply by some function, and that gives me my output Fourier mode. Okay, let's see. And then we just need to calculate what is h hat, and we'll fully understand what this filter is doing. So in order to do that, recall two pieces of information about the Fourier transform. Fourier transform takes a delta function to the constant all ones function, and it takes a function shifted to that function with a phase on it. We did the minus ik. Yes. Okay. So Fourier transform takes a delta function back and forth between the all ones function, and it takes a shifted function to the unshifted Fourier transform with a phase on it. And this lets us calculate the Fourier transform of this, because this guy's a delta function, and this guy's a shifted delta function, which means that Fourier transform of h, in other words h hat, is a 1 plus a 1 times a phase, so e to the minus ik. Okay, and we can just plot this function. So here's the modulus. It's part of a cosine, and now I've normalized everything, so we're at sample rate 1, so this should be up to 1/2. Starts at 2, goes all the way down here, and the angle of our function, the argument of h hat, is, I should have drawn my axis differently, a linear decrease down to pi over 2. Negative pi over 2. Okay, so this tells us exactly what our filter is doing. It's taking low frequencies and raising them, and it's taking high frequencies and kind of setting them to 0. So qualitatively, we would call this a low-pass filter, because it lets the low frequencies pass. So in particular, this is a bad low-pass filter for a number of reasons. One is that this is not the decay shape that you would like in a good cutoff function. Ideally, you would want something that really has a sharp cutoff at a frequency that you can, at some critical frequency that you can modulate as you want. And moreover, the kind of relative area where this frequency cutoff does happen is maybe, you might say around here, maybe the actual white curve here has a cutoff at that point, you might say. This is not a good cutoff level for audio. So if we kind of change back to the, if we undo our change of scale, so that this is going up to 44,100 over 2 hertz. Everything kind of above 10,000 hertz all sounds the same. Kind of the relevant range, like we hear logarithmically, so the relevant range of frequencies for our hearing is kind of more down here. And so this stuff is all kind of garbage that we don't care about anyway. But anyway, the point was not to make a good filter, the point was to give an example and kind of understand what it's doing. And now we understand what it's doing. Okay, so let's immediately pass to a more complicated example. So I want to introduce a new element to this class of filters that we're considering. That new element is going to be feedback, meaning that now we not only use input signals to construct output signals, as we just did here, and it's kind of covered up, oh no, there it is. We not only use input signals, but we also use previous output signals. Okay, so the example, and we're going to kind of stick with this example for the rest of the talk, is take the current input sample, take a scaling of a sample 3 time steps ago, and scaling of the last output from 5 time steps ago. Okay, so this is kind of the way you would write it if you were giving instructions on how to create the next time step from the data that you have available, or the next output sample. But let me immediately rewrite this so that we can kind of start analyzing it in the following way. I'm going to move all my y's to this side and keep all my x's on this side. Okay, and we see that now we can write both sides as convolutions. And let me write this as y convolved with h2, and this is x convolved with h1. Okay, and h1 and h2 are, h2 is 1 at 0 and at -5, so 1, 2, 3, 4, 5, I get some smaller positive dot here, and it's 0 everywhere else. And over here, h1 is very similarly a dot here, and then 3 samples back a scaled down dot, or delta, and 0 everywhere else. Okay, and now, once again, we're in business because we can take the Fourier transform of kind of both sides. We got y hat. I can, now that once we take the Fourier transform, everything's a multiplication instead of convolution, and I can rewrite all of this as h1 hat over h2 hat times x hat. Okay, and now to understand what this filter is doing, we just need to look at this guy. And in this sense, kind of this recurring theme of rewriting a filter as a convolution operator and just studying the convolution kernel, this is kind of a typical phenomenon where our filters are actually just other signals. We're just convolving with another signal, and all we have to do is study that signal to understand what the filter does. Okay. So, once again, each of these h1 hat and h2 hat, these are the Fourier transforms of very simple functions, like a delta function and a shifted delta function, shifted delta function. We can easily calculate the Fourier transforms of those with wherever I wrote those rules down there. And we get 1 plus 1/2. We get this over this, where I've done a little factoring and simplifying to make things look nice. Okay. And if we want, we can take this function and plot its modulus and argument. We get something that looks kind of like this. Very roughly, this is h1 hat over h2 hat modulus. Looks something like whatever, something like that. And the argument of of H1 hat over H2 hat, something like this. Okay, whatever. Not especially concerned about exactly what this filter does. It's kind of similarly just another example filter where we're trying to understand how it works. Okay, another thing that we can do with these circuits, or another way that we can understand them or represent them, is through an electric circuit. So let me briefly mention that and how it works. Okay, for this circuit, or for this filter, we take our input. Our input comes in, it splits into two things. One of these things says, wait 3 time steps, and after you come out of it, multiply by this scaling factor, 1/2 cubed. The other one just leads straight through. These give you your kind of initial output, and here output is yn, but then that output also feeds back into my input here, but before it does that, it has to go through this wait 5 box. Wait 5 time steps, and then once you come out, you get multiplied by 9 over 10 to the 5, and then you're in here. If I'm being careful, I should draw arrows to indicate which way my signal is going throughout. Okay, so it's not entirely obvious how to actually kind of run this circuit or how it works, so I'm going to give a very brief example. Let's say, look at the first 9 time steps. And as an input signal, let's just do an impulse. So it's 1 at time 0, and it's 0 at all other times. Okay, so how does this circuit work? At time 0, 1 comes through here. So 1's coming through here, it goes into this box, and it starts waiting for 3 time steps. And it also goes into this addition chamber. Nothing else is coming in here, nothing else is coming in here, so it goes out on its own, still 1, and it splits here. We get an output of 1, and a 1 also goes in and starts waiting in this wait 5 space. Okay, and that's it for time step 1. Now we had our output signal, and we have a 1 waiting in here and a 1 waiting in here. At time step 1, the next time step, nothing happens. There's 0 input. This guy's still waiting. This guy's still waiting. So nothing comes into here. We get a 0 output. Next time step, these guys are both still waiting. There's no input. There's no output. At time step 3, this guy's done waiting. It comes out, gets multiplied by 1/2 cubed. Nothing else is going into this addition. There's nothing from here. There's nothing from here. So this comes out, it gives us our output of 1/2 cubed, and it also feeds back into this waiting chamber. So now we have a 1 that's waiting here for another 2 time steps, and we have a 1/2 cubed that's waiting here for now 5 time steps. Okay, next time step, nothing happens. Also, I should point out now, everything over here is empty. There's not going to be any more input, and this waiting space is empty, so this part of the circuit is kind of done doing its thing. So now we're just looking at this feedback loop. At time step 5, the 1 comes through. We get 9/10 to the 5. That gives me my output, and that 9/10 to the 5 also goes in and starts waiting again. Time 6, nothing happens. Time 7, nothing happens. Time 8, the 1/2 cube that went through here is done waiting. It comes out, does this exact same thing. We get 1/2 cubed times 9/10 to the 5, and that same coefficient also goes back into here. Okay, so that's another way that you can write or represent these filters. before I keep going, I should check that this is still recording. Looks good? Okay. So, I haven't addressed it yet, but you probably already noticed that in this example down here, we have what appears to be a very nice polynomial in phases e to the ik or minus ik. And so instead of taking the Fourier transform, which turns time delay into multiplicative phases, we're instead going to take a kind of different, but very analogous type of transform that turns time delay into just a regular old variable, so that this actually does become just a polynomial. Okay. That transform is called the Z transform. And it's basically a generating function. You take, so what does it do? It takes our input function, or input signal, x of n, maps it to some output signal, capital X, of a continuous complex variable. And it's defined like this. X of z is the, I guess, negative generating function, z to the minus n, summing over all samples of n. Okay, and then let me remark immediately that capital X evaluated at z equals e to the ik gives you back the Fourier transform. So in this z plane, where our new z transformed function lives, moving along here gives you the Fourier transform. So the Fourier transform of your function lives on the unit circle in the domain of this transform. Okay, and another remark is that let me kind of just for the moment say capital Z transform of some function delayed by 1 is the Z transform of that function times Z inverse. So now instead of sending delays to phases, we send delays to polynomials. And this, of course, is exactly what you'd expect. You just get, right, this is kind of, if you have Z inverse here, on the Fourier side, this would mean getting a phase. So if we redo this example, so maybe I'll pass over here. No, this is good. Okay. Redo this example. Y of n plus 9/10 to the 5 yn minus 5. This guy. If we pass through kind of this whole same thing, we rewrite it as a convolution. There's a convolution way of, or the convolution also works nicely with the Z transform. Then what we end up with is taking the Z transform, you get capital Y of Z is this ratio of polynomials. So now 1/2 Z inverse cubed over 1 plus 9/10 Z inverse to the 5. Okay, so all of this just to kind of build some formalism around this idea that we want to turn this into a polynomial in phases. Okay, this guy has a special name. Maybe let me give some color. This guy is called the transfer function. Capital H of Z. And once again, this just represents everything that the filter is doing. Kind of in the Z domain, it takes your input signal, it multiplies it by this polynomial, and it gives you an output signal. And then you can take the inverse Z transform to retrieve your output signal. Okay, so now everything that we want to do to understand this filter can be just done through understanding this function H of Z. Okay, and now that we've kind of gone through this kind of construction, in order to turn it into a polynomial, we can do some nicer things with it. In particular, we can factor it. So H of Z, we can rewrite it as pulling out all the Z inverses and factoring and everything. We get Z to the 5 over Z cubed. And we get a bunch of roots of negative unity. So C3 here, when cubed, gives you -1. There's my numerator and my denominator. I have, I guess, 9 over 10, and a bunch of powers of C to the 5, or C5. Oops. And Z minus 9 over 10. There we go. Whew. Okay. So, what does this look like? Over here, this looks like, maybe let me continue using colors for a second. This guy, we factored it, so the numerator gives us a bunch of zeros, the denominator gives us a bunch of poles, so H of Z is a meromorphic function. Looks like it has 2 zeros at 0. It has, just look at my picture. Has zeros at these negative roots of unity, at radius 1/2, and then out here at radius 9/10, it has a bunch of poles at these 5 spots. Okay, so before we interpret this any further, let me make a comment that the fact that our filter coefficients, where is it? Here. The fact that our filter coefficients are real means that we have some real polynomial, real fractional polynomial here, which means that when we factor it, we get conjugate roots. And so conjugate roots on this picture kind of gives a graphical way of understanding why we only get half the data, or why our Fourier transform is Hermitian, because as we go around this circle, we're seeing the distances to these roots, and this is kind of, or how should I say? Okay, let me say it like this. So this meromorphic function, which is defined entirely by its poles and zeros, is some landscape over the z-plane, and because I have conjugate roots and conjugate poles, this function is symmetric over the real line, which means that as I pass around the unit circle calculating my Fourier transform, once I reach here, I kind of start to calculate the same thing, but in reverse, where the angle is now flipped, and the magnitude is flipped in the other way. Right, they're even and odd. Okay, so that's just kind of recalling that point. Now let me go on, because there's kind of a very nice interpretation of this. So let's see, if I want to calculate the phase response, or let me do it like this. So I want to calculate y of e to the I k over x of e to the I k. This is y hat of k over x hat of k. Let's say I want to do the modulus. So this is telling me, this is that modulus calculation that we were doing before. What's the kind of magnitude envelope of my filter? This is exactly given by the modulus of h of e to the I k, which, okay, we calculate this. This becomes, let me just write it out very simply. These zeros don't contribute anything here. We get product over the roots of the polynomial z minus e to the I, or e to the I k minus the root over the product of the poles e to the I k minus pole. Okay, and just to make sure that this is clear, the reason that this term doesn't contribute is because it's a pure phase term, so its magnitude is 1. Okay, so if we want to calculate our magnitude envelope for this filter, we just calculate the distances to all the roots and poles. So my picture for this over here, let me just redraw that exact same picture. I have zeros here, poles here, and if I'm calculating my Fourier transform to here, so e to the I k, this is going to give me my kth Fourier mode. Then, where did my green go? Any color. So I take the product of the distances to the roots. This gives me my numerator, these distances, and then, and of course the reason that the zeros now cancel out is because this is distance 1 no matter where you are on the circle to the center of the circle. And we divide by the product of the distances to the poles. So these distances. Okay, and that gives us the magnitude of our Fourier transform, which is a nice geometric interpretation. Meanwhile, if I want to know the argument of this, so if I want to know the argument of my filter at a given Fourier mode, I just need to calculate the argument of my transfer function h of e to the I k. And in this case, the argument function acts like a logarithm, so it splits products into sums, and I get, let's see, I get, looks like k squared from this guy, and, hey, I'm recording something, thanks, plus where did I write this? Okay, plus the sum over all my roots of the polynomial, the argument of this term, minus the sum over all the poles, the argument of e to the I k minus the pole. Okay. I'm out of space. I guess I'll try to squeeze it in. Where could I draw this? I guess right here. It's going to be very tight. Okay, but here's my pole zero diagram again. And now if I want to calculate the phase or argument to this point of my Fourier transform, let me maintain the same colors. So I sum the arguments to the roots, which means I add this angle, I add this angle, I add this angle, and also, let's say I also have this k squared, so I add twice this angle, or that should be 2k. Yeah, that should be 2k. Oops. 2k here, and then I subtract from that all the arguments to my poles, which means I subtract this angle here, this angle here, this angle here, this angle here, and this angle here. Okay. This is almost it for the talk. There's one last thing that I want to do, which is to give an alternate circuit representation. So, kind of introducing this machinery that let us write our filter in terms of a fractional polynomial gives this nice geometric interpretation of what the filter is doing. But it also lets us do something else which is nice and very useful in applications, which is to filter, what's the term? Factor a filter into a bunch of smaller filters. So currently our filter is a fifth order filter, meaning that it uses data from 5 time steps ago in order to calculate the next time step. And if we factor a different way, so this was a polynomial factoring, now let's factor by partial fractions, this is going to give us a way to decompose our filter into a bunch of smaller ones. Okay, so if also we factor by partial fractions, so this guy, 1/2 z inverse cubed over 1 plus 9/10 z inverse to the 5. If we factor this by partial fractions over the denominator, there are 2 ways that you might think to do this. One is to get it entirely in terms of like order 1 things in the denominator. So we factor it like this, factor the denominator like this, and then decompose by partial fractions. And that's going to give you a pole residue representation of this meromorphic function. But another way that we can do it, and the way that's relevant for the application that I'm thinking of here, is to pair up the conjugate poles down here so that everything has real coefficients downstairs. And so when we factor by partial fractions, we get real coefficients throughout. Okay, so when we do that, I'm just going to write a bunch of numbers. We're going to get 1 order 1 thing and 2 order 2 things. And the fact that we're summing them means that the equivalent circuit representation is going to be circuits in series. So whatever we can factor by partial fractions, this is like something that we're able to do. And this gives us an equivalent circuit formulation. So each of these on its own is a filter, and so has a circuit representation. And okay, the way that we've kind of made this Z transform, it's very easy to go back and forth between this representation of a transfer function and the filter corresponding to it. So if this is my transfer function, then the filter corresponding to this is, right, if you imagine there's like a y, there's a y on, all the y's are on this side, all the x's are on this side, these denominators move over to the y's. This is my convolution on the y's. So this gives me y of n, it should be Z inverse, minus 1.46 y of n minus 1 plus 0.81 y of n minus 2 is equal to, the numerator gives me my convolution with the x, 0.38 x of n minus 0.24 x of n minus 1. Okay, and this is, right, like the clear instructions for a filter. And since we've decomposed it like this, the largest powers the largest powers anywhere being -2, that means that we've written this as 3 circuits in series, each of which have order of those 2. Okay, and we can also draw a diagram for this, which at this point I would hand out, but since this is being recorded, let me just get it on the camera there. There we go. Okay. So that's it for this talk. Thank you very much for listening.